So, okay, the formal definition, and you can kind of make this for any category or any abelian category, is that the Bernstein center is just the endomorphism ring of the identity functor. Okay, so what is this thing, and what does it look like? So by Schur's lemma, so if pi is irreducible and z is some element in here, then, well, okay, then z gives an endomorphism of pi, and by Schur's lemma, that's a scalar, so then so, okay, to first approximation, this gives us, each element gives us some scalar for each irreducible representation, and we kind of want to understand how these scalars vary. So one thing that is true is that the center is, so let's see, if you have some ring, some associative ring R, and you have a category of R modules, then I think the center is literally going to be just the center of the ring. So our category is not R modules because this Hecke algebra isn't really a ring. But it is a limit of rings, and so the kind of analogous thing that you might hope is true. So this center is formally some like inverse limit of centers of these guys. Okay. Okay, so this is true, but the centers of these algebras can be very complicated. So this doesn't necessarily tell us that much. But I wanted to focus on two special cases first, so we can build some intuition. So the first is when G of f is compact. And then, that implies profinite, I think, in this situation. And for a finite group, the center, should literally just be a product of scalars over each irreducible. So in this profinite case, the same is going to be true. So in this case, Z rep G is just like this. And then you might be wondering, oh, okay, so is this just like what it's going to look like in general? But that's not true. And the next example is supposed to illustrate that. So the next example, I'm cheating. I'm going to consider smooth representations of Z. Well, Z is not really one of the groups we're considering. But the reason I'm interested in this is because QP cross is isomorphic to famously ZP cross and, well, sorry, that's not what I want to say. What I want to say is Z given by the uniformizer and then some compact group. So if you wanted to understand what's going on in the QP cross case, then you better understand what's going on for Z. So that's why I want to talk about that example. Okay, so rep Z is in bijection with C cross. And the point is that in this case, so in this case, there's some universal character, chi univ, and it looks like the following thing. So we'll think of it as a map like this. And it has the property that if you take some point in here, okay, that gives you some representation. Let's call that representation chi s. And I'm writing it, so it's a character, so it really is valued in C cross, but I'm writing C intentionally. And then, but But this is a point of this algebraic torus, and so it will also give us a map going this way. And the point is that this diagram commutes, so this is the universal property that this this is the property that this chi-unif has. And this is a representation, so this becomes a representation of z acting on the left, let's say. And so what I want to do is I want to take a z I want to take a z in the center here, and I want to see how z will act on this chi-unif. And well, whatever the endomorphism it gives, it's z-linear, so it actually has to be cz linear. So the point is it has to actually be an element of cz. So acts by an element of cz. And I guess my point here is that this is way smaller than you might expect, right? So a priori, the representations are in bijection with C cross, and so you might think that you can just assign some scalar for every point in C cross, and that there's total flexibility. But this is showing us that that's not true, because the point is whatever endomorphisms you get, it has to be functorial. And so the fact that z acts on chi-unif by some element here, we can figure out how z acts on any given character by this map S. And so in particular, what this is saying is that the scalar has to vary as a regular function in this torus. So this is the key observation. And so what actually ends up being true is that in this case, the center is just CZ, which we'll think of as the regular functions on this one-dimensional algebraic torus. We're taking representations of the group Z, and let's think, what? With no other conditions.
So vector spaces with an endomorphism.
Yeah, I mean, it's not. So in particular, I said it's in bijection, or the irreducible, okay, maybe you're upset that I wrote C cross here.
Okay, cool. Okay, well, you should write irreducible somewhere.
Irreducibles, yeah. Thank you, yeah, right. It's not true, yeah, okay, good. Yeah, thanks for the question.
Also, in this case, rep Z really is modulus of a ring, CZ, so that you already said what the Bernstein center was.
Yeah, that's true. Thank you. Yeah, I guess, but okay, so.
You must have had some reason.
I had some reason, yeah. So, and my reason is that, well, this is, so this kind of argument that we just did is exactly the argument that Bernstein, so in the suggested readings, there's this article of Deline that explains how this works in general, how to compute this Bernstein center. And this is exactly the argument that is used, but I just dumbed it down to the Z case. And so this is what you do. And also, my other motivation is that these universal unramified characters are going to play a big role in what is about to come. But yeah, that's a good point, Jared. If we just wanted to know what the center is, there's an easier way to do it. Thanks. Okay, so what's the general structure? So, yeah, so firstly, okay, so firstly I want to define some group G0 of F, and I want to define it in the following way. So firstly, there's a map G to G mod the derived subgroup. And this is some torus. And then what I want to do is I want to take, so this thing is defined to be pi inverse of okay, hold on. Let's put a circ here. And so this is the maximal compact of the torus. So this will give us some subgroup of G of F, and then what I want to say is the character is unramified. If it vanishes on this space. Okay, fine. And so in particular, this space of unramified characters, so so there's some algebraic complex torus, which is kind of the space of these unramified characters. Okay. And then I want to say that a cuspidal support datum M sigma is a pair M sigma where M is a Levy subgroup. And sigma is a supercuspidal representation of MF. Do I want to say irreducible? Sure. I suppose I should. Yeah, and so what is this cuspidal support datum? Well, the point is that if you take an irreducible representation of G, it will show up essentially uniquely in the parabolic induction from M of some supercuspidal sigma. And so this is telling you. So you could imagine attaching to each irreducible representation pi of G of F some such cuspidal support datum. And then further, I want to consider an inertial equivalence class. And so this is an equivalence class on cuspidal, this is an equivalence relation on cuspidal support data. And what is the equivalence relation? So M sigma is equivalent to M sigma prime if they're conjugate and if...
So it should be an M prime also.
M prime, thank you. If they're conjugate and if the conjugation can induce an isomorphism. So M conjugate to M prime. And it induces an isomorphism between sigma and sigma prime. That's not correct.
You want to allow some...
Up to a character chi, such that chi is unramified. Okay, so we're now allowing ourselves to vary these cuspidal support data by an unramified character. Okay.
How's M, not a P?
M. It doesn't make sense, right? Well, okay, I guess you could restrict. Oh, geez. Okay. So then the theorem is that this is the theorem is that the center is exactly this. So you take you take a product over all the inertial equivalence classes of cuspidal support data, and then there's some torus that I'm about to tell you how to get it, and then you take the regular functions on that torus. So how do we get the torus? Well,
Shouldn't there be some finite group acting somewhere?
that's the torus. Okay, wait, hold your horses. Okay, so T m sigma is going to be the quotient of x unramified m by stab sigma. Okay, there's like some torsor here, right? But
It's not usually a torus.
take a further quotient by, you need to take a further quotient by some vial as well.
really?
Yes. Like for GL2 and the torus and the trivial character, you get the torus you wrote down there is the torus of unramified characters.
Mm-hmm.
And you have to act on that by, you have to take the quotient of that by the vial involution.
Mm. Okay, that seems believable.
So these aren't usually tori.
What?
These aren't tori.
I thought if you quotient a torus by a finite group, it's still a torus.
Finite subgroup of the torus, yeah, but not a random group of polymorphisms.
Okay, I apologize for this.
If you put like a superscript random finite group on that curly O, I'll be happy.
What?
On the curly O in
Yeah.
the product, like there's some finite group acting and taking variance.
Okay.
Maybe G is that better. Yeah.
Okay. All right. Thanks. Okay. So I wanted to say a little bit about this stab sigma, at least. So first of all, W is some vial group action that David Helm has told us about.
You look at those elements of the normalizer of M mod M that conjugate sigma to an unramified twist of sigma. And that acts on this torus of unramified twist.
Yeah, okay, fine.
Basically, first you have a torus where you say, what are the unramified twists of M?
Yeah.
And then you ask, and that's the quotient by stab sigma. And then you ask which unramified twists of M give rise to the parabolic inductions that have the same Bernstein center action. And that's this vial conjugation.
Okay, and this was the finite group that
ruins its toric nature. Yeah.
that ruins its toric nature. Okay, thank you. I'm happy again. Okay, fine. Yeah, but so, okay. Well, so there's a map from X unramified M to, so you can restrict to the connected center of M. And the point is that stab sigma has to live inside the kernel of, like, let's call this map res, then it has to live inside the kernel of res, because basically if you don't live in the kernel of res, then when you twist by your unramified character chi, you're moving the central character by some amount. And so this stab sigma has to lie in this kernel, but actually this kernel is like some finite thing. So this stabilizer has to be very small. And so some example of like you can consider is in this like GL2 case, there's a character theta that so we take the determinant and then we get a QP cross and then there's a Z in there, and it maps 1 in Z to like -1 or something like this. And if you think how this character will act, it will fix like certain supercuspidals that come from like a degree 2 unramified extension. So it's not, so I wanted to say something about this because you see this stabilizer showing up and there are simple examples of it, but like it's not, so like, of course this map for a torus, if M is a torus, then this map is an isomorphism, then there's no kernel, then there's no stab sigma. And also if your group is semi-simple, then this ZG circ is trivial, and so then, yeah, okay. Like if your group is semi-simple, there's really no unramified characters, and so then again, there's not much of a stab sigma. So this is an example where it shows up, but okay. Okay. So one consequence of this discussion is that rep G decomposes as a product. Like this. Right, because this ring has a big product structure, and so it kind of decomposes the whole category. And these things here are what are known as Bernstein blocks. And so what representations show up in a given Bernstein block? It's like, well, just by kind of definition from what I've told you, it's representations pi where the cuspidal support is some unramified twist of M sigma. Okay, so a standard example is like, is like if you take the Levy torus and you take the trivial thing, then this is what people call the principal block. G split. Let's not take risks. All right. Okay. Well, then what is the theorem I want to say? So the theorem is that you can take sigma and you can twist it by this universal unramified character for the Levy that we saw before, and then you can parabolically induce. And this is a projective generator for rep G M sigma. Yeah. So how would you prove something like this? Well, okay, so let me not really prove it, but let me just give you some ideas. So for the projectivity, you first show that this thing is projective. As a rep of M. And then what you want to show is that this takes projectives to projectives. And this follows from second adjointness and the fact that JPG is exact, I claim. And then for the generator, So we need to show that whatever this thing is, if you take some irreducible in rep G, so if you take some irreducible in rep G M sigma, then you want to show that there's a map. You want to show that there's a map like this. And so how do you do this? So again by second adjointness, there's some map like this. So there is just formally some map of this form, and then you can take some irreducible row in here, and so then you have a map. You can take some irreducible row that maps to pi, so then you get a map like this. And then you just need to show that sigma chi univ maps to rho, and then you can apply induction to this map, and then you can compose, and you'll get a map from this projective generator to pi. Okay, so anyway, so this proof of this theorem is an exercise in second adjointness. Once you know second adjointness, and you also need some fact about like supercuspidal representations. Yeah.
This kind of universal is valued in the proof ring, no?
Yeah.
So this is a statement of our representations with coefficient.
Well, your tensor, it gives you some representation, and you tensor the representation you started with this group ring. And you get, I mean, it's in particular a complex vector space, right?
Okay, I see.
Yeah. Okay. And I go till 45 or something? Okay, good. Okay. So what is some corollary of this? Some corollary is that rep G M sigma is equivalent to the category of modules over the endomorphisms of this projective generator. And so a priori, it may not be so obvious what these endomorphisms look like, but here is the following claim. So the claim is that in this case, so now I'm reducing to a specific case. So I want to consider M is a Borel, sigma is trivial. So, sorry, M is a torus, sigma is trivial. And I want to fix in like an Iwahori subgroup. And then what we will get is that this is isomorphic to this compact induction of the trivial representation from this Iwahori. And so then this implies that rep G T1. So this implies that this principal block from before is isomorphic to modules over this. But then this already showed up earlier in the previous lecture. So this is just this is exactly this Hecke algebra for the compact for this Iwahori. So this principal block corresponds to modules over this Iwahori Hecke algebra. Okay, so I guess my plan for the next bit of time is to discuss how we might prove this claim, how we might show this isomorphism. Any questions at this juncture? Yeah.
Are you going to say what I is?
So, sure. So I'll say for GLN, how about that?
Well, you fixed it D. I is the stuff that lies in D modulo the uniformizer.
Yeah, okay. But go ahead.
So you don't look happy.
Well, it seems you need integral models for
Yeah.
the group, the group in particular. So I guess we lost some generality.
You should be on room, but
Yeah. So, yeah, so in this case, there's a reduction map. And then you can just take, the preimage of the spiral in the thing, and that will give you some Ihori. So, I mean, in general, you can pick some point in the building corresponding to some integral model, and then you can do the same reduction, and it's like the same. Other questions? Okay. So I'm going to say a tiny bit of this like Bushnell-Kutzko type theory. So the first definition is that we say that a pair So if we have a pair like this, then we say that it is a M sigma type. If pi is in this block exactly when the Homs to the restriction of pi to k is non-zero. Okay. So this seems like maybe a fanciful thing to hope for. But actually, in many, many cases, we have existence of these types. So let me say a tiny bit about that. So the first fact is that if if we have a supercuspidal block, and that supercuspidal is like some compact induction, as I said before, of this form. Such that K tilde is compact mod center. Then you can take K to be a maximal compact in K tilde, and you can restrict tau to K, and this is a G sigma type.
is that restriction irreducible, or do you have to take like a random constituent?
Oh yeah, I guess it needs to be irreducible. Maybe you can just take a constituent. Oh, but that shouldn't change. I feel like that shouldn't change the reducibility because Okay, let me not speculate. Okay. And in particular, in this case, then, rep G M sigma is, so I'm introducing some notation here, is equivalent to the category of HGK tau modules, where this HGK tau is then this thing. So this is like a tau twisted Hecke algebra. Fine. So the first thing is that when you have a supercuspidal block, like we actually, in many cases, for instance, like when G is tame and P is not bad, then we actually have descriptions of supercuspidals as compact inductions like this. And so then we have types. So these are the supercuspidal types. So the next thing I want to talk about is G covers.
Are you going to go back to the equilibrium at some point?
Yeah, that's this is all, it's all happening. Yeah, okay. And I just forgot about that. Okay, so this is a definition of Bushnell. Let's go. Oh, I'm going to prove something much more general, and then I'm not really going to prove anything, but okay. So suppose M is a Levy subgroup of G, and suppose we have two pairs, K tau and Km tau m, such that Km is just this intersection. So blah 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 blah. So K tau is a G cover of Km tau m if tau restricted to Km is tau m, and then for all parabolics of M, we have K is exactly like K is exactly like this group. So P is, again, this is like the Levy decomposition. And then also we need that these restrictions are trivial. Plus,
Sorry, you said P is parabolic of M, but then P is M times U.
It means parabolic containing them.
I'm sorry, yeah. I mean, it's a parabolic with Levy M. Yeah, okay, I see now that is confusing. Okay, plus, let's say a technical condition. So, okay, so a G cover is of some pair is some other pair satisfying these properties. And what you're supposed to be thinking of is that, so the Iwahori and trivial is a G cover of T0 and trivial. So there is some like factorization of Iwahoris that I'm kind of invoking here and not proving for you, but okay, fine. So then, the theorem of Bushnell. So first of all, in this situation where you have this G cover, you get an induced map of the twisted Hecke algebras. And the theorem is that Km tau m is a m sigma m type implies K tau a m sigma G type. So okay, I said that for these supercuspidal blocks that we often have types, and then this theorem is supposed to tell you that, okay, well, if you can produce a G cover, then you also have types for these non-supercuspidal blocks. I'm missing a K. Thank you, Yuji.
But also you have to assume that this is a cover situation, like it's in the definition.
Yeah. K tau, a G cover. Thank you. And furthermore, you have a commutative diagram. Of the following. So this horizontal map is the equivalence okay. So this is saying that, okay, so in each of these cases, when you have types, you get an isomorphism of your category with some module category. And this is saying that you can induce and then pass through this equivalence, or pass through this equivalence and then tensor with the Hecke algebra. And so here, to do this tensor product, I'm using that you have a map of these Hecke algebras that I said happens in this G cover case.
So the horizontal arrows mean restrict K and home from?
Yeah, exactly. Yeah. That's how the equivalence is set up. Yeah, right. Thanks.
Horizontal arrows are equivalences.
What?
The horizontal arrows are equivalences.
Yeah.
Can you notate that?
Okay. So what is some corollary? So let's do some computation here. So let's take IGP op C int. So what I want to do is figure out what this commutative diagram says for this particular representation that is this compact induction. This is going the top way around the diagram, and this should be the same thing as going the bottom way. And that's this. So I'm slightly compressing the notation here. Okay. But the way this equivalence is set up is that this representation itself goes to exactly this like twisted Hecke algebra. So this is the same thing as hm tau m tensor over hm tau m of hg tau. And this is just hg tau. So this says that, okay, and then as Dave asked me to notate, this tau functor up here is an equivalence. So we can figure out, well, hg tau, we know what that corresponds to. It corresponds to this compact induction like this. So what we've ended up proving here is that this is the same thing as this. So the opposite parabolic shows up because like there's a second adjointness somewhere. But yeah, okay, maybe I shouldn't. But just to say that it matters for this diagram, but it doesn't matter for what I'm telling you because there's really no choice. The choice of parabolic doesn't matter, right? So you have a parabolic that you care about and then you just take p op of p op or something. And yeah. Yeah, so in fact, good. So let's remove that. Okay, and so in particular, so in the Iwahori case, well, on the one hand we get this, and on the other hand we get I, B, G, and then we take the compact induction from T0 to T of the trivial. But this is exactly chi-univ. This is exactly this universal unramified character. So this kind of computation shows us this isomorphism in this case. So okay, so why would we care about this? Well, one reason is that now we can more explicitly describe this, in this situation, this gives us a better way of describing this, this block as modules over a more understandable ring. But the other thing is that these like projective generators, these IPG sigma chi-univs, that they show up a lot in the theory. In particular, like in this Iwahori case, this thing eventually gives us some sheaf that is like the coherent Springer sheaf. And maybe natural generalizations of the coherent Springer sheaf are related to these like other projective generators. And so it's very important that we have this explicit description of what the endomorphism algebra looks like. So I think this will show up in other talks as well. Yeah. Okay. So I guess that is roughly what I wanted to say. Yeah.
So in the earlier career diagram, so like you could change the parabolic, but I think that also changes the map between these two Hecke algebras, right?
Mm-hmm.
Can you explain how this map is induced?
Yeah, maybe we can talk. What?
We better not.
Yeah, we better not.
You can imagine there's like different left versus right module structures here that one has to choose.
Yeah.
Somehow those symmetries match with this choice.
Yeah, thanks.
Can you say a few words about how these Hecke algebras are like really nice things that Bernstein proved about them?
I don't know.
The endomorphism rings of these projective generators.
What do you want me to say about them?
Well, like, how does this relate to the Bernstein center, for instance, that you started with? If you go up, right, you have this more. Yeah, you have that this block is modules over this endomorphism ring.
Mm-hmm.
Like, can you say something about how that relates to like the center?
So I don't know. I don't want to say something wrong, but I guess the center of this should be related to the center up here, like this thing.
Yeah.
Yeah.
No, it is literally that.
Yeah.
That's,
Other comments? Yeah, I guess if you believe this like ring thing that I said before, then you would just immediately know that or something. Yeah.
And when you're showing that the projective generator part,
Mm-hmm.
where for the generator part, where did you use the condition that pi is in this particular Bernstein block?
other way.
Right. So, well, the point is we want to. So the point is that we want to construct a map from this projective generator to pi, and that is only going to be possible if the cuspidal support of pi is some unramified twist of sigma. Right? If the cuspidal support of pi is completely unrelated to sigma, then these things will have no map. And so that's so explicitly like you won't be able to find. I mean, because the induction from p to g of rho maps to pi, you won't be able to find a map from sigma chi univ to rho unless like pi is in the correct block.
So what is rho here?
Rho is some irreducible inside of this Hecke module of pi, right? So we know that here we know that the induction of this whole Hecke module maps to pi, and so we want to say, okay, so we want to take the Jordan-Holder decomposition of this Hecke module, and we can argue that some piece in this Jordan-Holder decomposition, the induction also maps to pi, and rho is irreducible. Yeah. 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 Okay, great. Thank you. So I didn't completely hear what you said. But I wanted to, so I thought what you were saying is, can you relate this talk to this cohomological duality in the previous talk? So the answer is yes. So thank you for this. Right, so in the previous talk, this d pi showed up, this degree. And in the Steinberg, after some prodding, we got that it was 2. And what is this degree pi? It should be the dimension of that particular piece of, so our pi corresponds to lives in some block because it's irreducible. And that block will be of a certain dimension. Like it'll be the regular functions on some variety of a certain dimension. And the d pi is exactly that dimension. So that's like kind of a connection.
It's also the rank of the split center of M, where M is that M period in the block become.
Right, exactly. Because we took this unramified torus and we made some finite modifications of it, but nothing there changes the dimension. So yeah, as Dave said, it's just, so that's how you can see like immediately in this Steinberg case that it's in the principal block. The torus the space of unramified characters of the torus is rank 2, and so then this D Steinberg has to be 2.
The D pi from the first lecture is the split rank of M at the end of its series. Yeah, that's right.
Yeah, but that's fine.
But that's still
We have to count that as well,
Yeah,
I think.
it's
Yeah.
correct even if M is G.
Think about representations of a big torus.
Yeah.
This naive way
Oh,
is like
oh, yeah, no, you're right.
you solve
You're right.
the duality on this torus.
The what?
Like this decomposition duality is at least under this isomorphism for certain regular functions on tori. This is just parabolic duality.
I'm not sure. The question was if this cohomological duality is related to growth and Dixer duality on the torus. I don't know. Does anyone want to chime
Some
in?
relation.
Dave says
This
there's.
is a full categorical story, but
Dave says there's some relation. I mean, we're going to see a lot more about these dualities in further talks when we have when we can talk about Bun-G, for instance.
maybe one more quick comment is that like everything you said kind of extends immediately to the derived category. If that
Yeah.
also has a block decomposition,
Mm-hmm.
the same indexing set, and the same generators even.
Mm-hmm.
Like no further work needed. That'll be it.
Thank you. Did everyone hear that? Make a note. So the comment was just that everything I did here kind of extends to the derived category with the same indexing sets and generators.
Is that true for any abelian category that is a product of other abelian categories?
Probably
Is that a
big
question
problem.
or? Like, is it a formal consequence of?
Maybe you'd want enough projectives or something like that. I don't know if it holds without that. But, yeah.
Maybe.
There was some discussion of what is the center for the derived category. Like you can take this endomorphism algebra of the identity functor, because it's an R-Hom, and you could just take the H0. And at least in the ring case, that should recover the center of the original abelian category you started with. Other questions?
So maybe we'll see it in later lectures, but I mean, at the end you mentioned some relationship to coherent Springer sheet.
Mm-hmm.
Are you willing to give us some preview? Or?
Well, I think that David, are you?
That will be Thursday.
Yeah, I think this will be discussed probably extensively, hopefully. It sounds like you're going to talk about it. If he doesn't, it will be talked about next week anyway, so.
I think this will be a recurring theme.
Yeah.